Welcome to this explainer. Today, we're diving into some incredibly fascinating new research that takes the, let's be honest, historically intimidating world of quantum physics and makes it, well, totally accessible. And it does this using just simple arithmetic. We're talking about a recently published paper with the somewhat heavy title, A Term-Rewriting Semantics for Pure Quantum States. Now, if that sounds like a mouthful, don't worry. The core premise here is actually all about simplifying things. We're going to explore how beginners can grasp the very heart of quantum computation using nothing more than basic math. So think about this. Can middle schoolers do quantum physics calculations? I mean, most of us would immediately say, no way. We know how notoriously difficult quantum math can be, right? You probably picture massive chalkboards just covered in complex calculus, linear algebra, weird Greek symbols. Basically, we assume quantum mechanics is locked behind these heavy doors that only PhD students can pry open. But as you'll see, this research challenges that exact assumption. To understand how we actually get there, we first need to look at the main obstacle. That brings us to part one, the quantum math barrier and how we overcome it. Traditionally, anyone trying to study quantum theory just slams headfirst into a massive wall of complex and, honestly, sometimes irrelevant-seeming math before they even get to the actual physics. It acts as a huge barrier to entry. But this paper explores a really clever alternative known as the misty states formalism. Now, this approach relies entirely on accessible, simple arithmetic. It completely bypasses that initial math barrier, which lets first-time learners get straight to the physics and the logic of quantum systems without getting immediately bogged down in all that traditional mathematical apparatus. So, what exactly is this alternative? Let's dive into part two. Enter the misty states, a totally new framework. Now, this concept didn't just pop up overnight. Back in 2017, researcher Terry Rudolph originally introduced this idea of misty states as a way to accurately describe the basics of quantum circuits to high school and middle school students. But look, don't mistake this for a mere child's toy. This framework was built to take advantage of a truly remarkable mathematical result by Yayan Shi, which itself leveraged another powerful result by A.Y. Kataev. So the foundation here is incredibly rigorous. It ensures that simplifying the math doesn't compromise the underlying truth of the physics. And that brings us right up to July 2026, where author Dan Adrian German published the paper we're unpacking today, which takes this framework and extends it even further. Okay, so how does German actually define a misty state? Well, formally, it's an elementary rewriting system providing term rewriting semantics for pure quantum states. But let's put that in plain English. Instead of dealing with dense matrices and continuous waves, you're essentially just swapping out terms based on a set of simple elementary rules. It's kind of like a giant structural game of find and replace, and it perfectly mimics the behavior of pure quantum states. Of course, that brings up a pretty natural concern, which leads us to part three, simple arithmetic, accurate physics, and how they maintain rigor. You see, simplifying the math definitely does not mean dumbing down the physics. Beyond those rock-solid foundations we just talked about, this system achieves what they call good enough accuracy, and it does it using a tiny, universal set of gates. And honestly, having a universal set of gates is a massive deal. It means you aren't just limited to basic textbook examples. You can literally use the misty formalism to process any complex quantum calculation. Sure, it might require a small overhead, a few extra steps here and there, but the capability is absolutely there. It's a fully functional, highly accurate sandbox for exploring quantum behavior. So, with that robust foundation firmly established, let's look at Dan Adrian German's new 2026 paper. Moving on to part four, expanding the misty universe, pushing the boundaries. German's new paper actually takes this framework quite a bit further, breaking it down into four distinct steps. First off, he reviews the original 2017 proposal just to establish what worked and, what needed a bit of improvement. Then, he really puts the system to the test by demonstrating actual entanglement swapping. This shows exactly how quantum particles can become linked even without direct interaction, which is wild. Third, he introduces a brand new category of what he calls irreducible misty states. These basically act as crucial fixed points that stabilize the entire system theoretically. And finally, he tackles the GHZ game. For context, that's a classic, highly complex demonstration of multiparticle quantum non-locality. I really want to emphasize just how profound this is. We're talking about deeply non-trivial phenomena here. Things like entanglement swapping and the GHZ game are being modeled with basic arithmetic. The fact that a first-time learner could grasp these advanced mechanics simply by rewriting terms, it just shatters the traditional barrier to entry. It proves that the actual logic of quantum mechanics can be understood way before mastering the advanced mathematics that are usually required to express it.
But there is an important caveat to all of this, which brings us to part 5, the bridge to standard theory, using this as a stepping stone.
The authors are actually very clear about their intentions here. They explicitly note that the MISTY formalism can effectively be used to facilitate a transition to the full conventional quantum mathematical apparatus. So they aren't advocating for recasting all of quantum theory into this MISTY formalism forever. It's not meant to be a permanent island. Rather, think of it as a bridge. It's a highly effective way of getting people straight to the heart of some seriously non-trivial quantum theory first. It sparks that understanding, it builds that intuition, right before they cross over to tackle the really dense conventional math. And I think that leaves us with a truly inspiring question. If simple arithmetic can unlock the heart of quantum theory, which is literally one of the notoriously most difficult subjects in the world, what other complex scientific barriers could we bridge next? How many more people could we invite into the scientific community if we just rethought how we present the foundational math? It's a powerful reminder that sometimes the absolute best way to understand the complex is just to find the simplicity hiding underneath. Thank you so much for joining me for this explainer.